Good afternoon, everyone. My name is Amy Che. I'm a Principal Solutions Delivery Manager. I'm part of the Solution Architecture org at AWS. And we're kicking off this afternoon with Amazon Aurora. How many of you guys were here for the morning session on RDS? Is it everyone? All right, cool. So I'm going to probably skip through some stuff that was covered in the morning on relational database services. And we're going to focus in on Amazon Aurora. I've been at AWS for about 3.5 to 4 years now, so I've had the pleasure of watching our services grow exponentially, and trust me, it's really hard to keep up with everything that we've got. So lots of great content. Hope you guys stay engaged. So this morning we talked about relational database services, or RDS, and as we probably mentioned from Vlad, we talk about choice, we talk about value, and we talk about innovation. And so what we like to do with these three themes is we like to always talk about how we take this built-out RDS and then how we leverage this within Amazon Aurora. So getting into the first point, when we talk about the value, we bring 7 different databases. I'm sure we covered a lot of it this morning, but we start out with your open source database engines, which I'm a big fan of. I originally worked at Red Hat, so I love open source. Amazon loves open source as well, and so we support, MySQL, MariaDB for those of you who wanted to venture away from MySQL, and Postgres. For your commercial database engines, for something that you want that happens to be more highly available, more scalable, we have Oracle and SQL Server. And then for our cloud-native engines, what we did was we built a cloud-native engine, Aurora, built off of open source databases, leveraging the cost and efficiency that you get from there and taking the high performance and availability you get with the commercial engines. And that is Aurora. And with all of that, it's on our RDS platform where you get all the various things at the bottom managed for you. So Amazon Aurora is delivered as a managed service. Again, I won't cover this too much. I think you heard about a lot of the RDS in the morning, but Amazon Aurora, what we like to say is that leveraging all those pillars that we talked about earlier, you have the speed and availability that we talked about from those commercial databases. You get to have the wonderful cost that we have open source development. A lot of our engines, we take actual open source engines and then we will fork a branch and we'll continue to help contribute back to open source while we maintain and update our database engines themselves. And you'll generally see about a 1 to 2 month lag between open source contributions and our taking it in within our engines. And then we have the compatibility because we are using those open source engines in the background. And you pay for what you use. So getting into the innovations, we like to talk about scaling out, having a distributed multi-tenant design. And so this gets into when we talked about our availability zones, which are more or less a data center within a metro area for an availability zone. So you could have more than one data centers, but generally the easiest way to think is an AZ or an availability zone is a single data center, and then a region is an entire geographical region. A service-oriented architecture, and then we like to talk about how we automate those administrative tasks. So scale-out distributed architecture. We have a lot of services at AWS, and relational databases in general hasn't changed that much since they started coming around in the 50s or so. They weren't designed for the cloud. They started on-prem. You started out working with these large-scale mainframe Unix systems, and we slowly evolved them over time. But traditionally, from an architectural standpoint, they started out with an on-premise architecture. There's multiple layers of functionality. They all reside in this large monolithic stack, typically on a single box. So you would have like a SQL layer, a transactional processing layer, caching, logging, and a storage layer. So you have quite a few layers involved. And so when we talk about your logging and storage layers, we took those at AWS and we created a distributed log structure which allows us to have a purposeful built for the database. So we separated the compute part, the engine, from the storage, and that's what makes Aurora unique. So if you look at the storage layer for Aurora, it's spread across 3 availability zones, which I mentioned are essentially data centers within a region, within a metro area. And then we shard the data, which means that we slice all the data up and we spread it across the different availability zones, and then we bring it down into storage volume layers. So you have 6 copies of data sharded out, and then we take 2 copies and we spread it across each availability zone. So if you have failure in any AZ due to whatever reason, whether it's nature-related, power-related, network-related, you still have access to your data from something else. And then we apply those principles to the other layers of the stack as well. And so the other thing that we did with our scaled out infrastructure is we said we wanted to leverage what we have. So the benefit of building our database on top of AWS services is that it integrates easily with our other AWS services. So for example, with Lambda, we have Lambda baked into Aurora, and you can invoke Lambda functions from within Aurora itself for your stored procedures and your triggers. For Amazon S3, that's what we use in our storage layer. So for that, we use it for a backup, and we continuously back up your data all the time. Fantastic for recovery. And also, we're integrated with IAM, which is our security policies. So you have layers of your database integrated with IAM, so you can lock down how you're accessing everything with the identity and access management. And then we also are integrated with CloudWatch for all your monitoring and logging, and we're automatically uploading that data into the clouds and storing within S3 as well. And so these are just some of the services that Aurora integrates with. Automated administrative tasks. How many in this room are DBAs? How many of you guys like having to do all the backups and the restores and having to do the point-in-time recovery? You actually like them. You would be one of the few people. I used to be a Unix AIX and a Solaris admin back in the days before I went over to Red Hat. And I remember having to do some light database admin tasks, and they were not fun, at least from a general sysadmin point of view. So what we like to do is we try to take all those repetitive manual tasks, and we wanted to automate them and remove that heavy lifting from you guys and let you guys spend time where it's more interesting. So if you look all the way over on what is your left-hand side for the AWS part of the portion, it's everything that we do for you. So this is about, I think, 7 different things that we cover automatically as part of Aurora on your behalf that you no longer have to do. I think developers, especially developers who have to do development and admin, operations, all of that, they're probably excited about this. The things that you are left to take care of is you get to focus in on those schema designs, probably more interesting to figure out like a puzzle, right? You get to work on your query construction, and you get to work on query optimization. So instead of having to spend time on doing the backups, on the recoveries, on making sure that you're failing over to the right ones and trying to make sure that you hit all those compliance and all the auditing over and over and over, you get to just focus in on more interesting, hopefully more beneficial tasks for you. We are still the fastest growing service in AWS, Aurora specifically. Those are some of our customers that we are allowed to actually talk about. I'm not going to drill into them. As you can see, we have a lot of customers of various sizes and industries represented. So who's moving to Aurora, and why are they actually moving there? So you can break them down into 2 categories, right? And it goes back to how databases are. You have your open source side of the house, and you have the commercial side of the house. And they generally want their engines for different reasons. So the open source customers are the ones who use the open source databases. And so they want it because it's a cheaper option. You have flexibility, you can do tweaks, you can have a smaller database node to save money or even go serverless. If you look at the commercial side of the house, right, they're there for different reasons. They're there for the scalability that you have, because they know that it covers that large-scale enterprise distribution, and you can do amazing performance optimization with it, and they have these great tool sets with them. So we covered all of that with Aurora. With Aurora, whether you're using MySQL or Postgres, are two main flavors of Aurora, you still have better performance. You have up to 5 times the performance on MySQL. You have better availability, durability. The cost reduction, it's actually a significant cost reduction, even when you're comparing to open source, depending on how you're using them. And we'll get into that a little bit later. And we also provide the tool sets to help you move between open source and commercial to RDS and Aurora. So let's talk a little bit about performance and talk about some benchmarks. So this graph is based off of Sysbench. So we did some tests on using MySQL for Sysbench, and as you can see with MySQL 5.6 and 5.7 against their equivalents within Aurora. And those are the 2 versions of MySQL we are currently compatible with. So you can see the performance difference for when we were running the different types of throughput here. So you have your write throughput and your read throughput for a comparison. The other part of throughput is there's also your data loading performance. So here is when we're looking at Postgres. So this includes loading your data, vacuuming, and building your indexes. And this can be done up to 2 times faster. So if you look at the same numbers for loading your data for MySQL, it's about roughly 2.5 times faster. It's faster to load the data than to actually process it. And another thing to know about the throughput is it's also more consistent in the throughput. So if you look at the very bottom, the orange line, that's Aurora's performance for loading the data under a high load. The blue line is how Postgres was performing in the same scenario, and you can see a lot more variability going through all of that. And so by the standard deviation, it's roughly about 10 times better. So again, here it is for MySQL versus Aurora MySQL. Again, the orange at the bottom is Aurora, and the blue is, in this case, MySQL. So on top of the performance that we've been working on, we said, what else can we do? And so we said, throughput, loading data, that's all software improvements. So we also looked at the hardware and said, what can we actually do to improve from the hardware perspective? So we started out, if you look all the way over at the far right-hand side, we started with 8XLs. And that was 32 vCPUs at 256 gigs of memory. And that's what we started out about 5-6 years ago from a hardware perspective. And so that roughly translated to giving you over about 100,000 writes per second. So now, as of the end of 2018, we support 16XLs. And those have 32 vCPUs, and they have about half a terabyte of memory, which means that we get 200,000 writes per second, doubling the performance. And with the read performance, we started with 500K reads per second. We are now at 700K, and the reason why we weren't able to quite double the performance is we've got limited by actually our network capacity on the insides. So we're soon going to be launching the 24XLs, and so you can see we're going to have even better performance, and hopefully that will be on the roadmap for this year. So how did we achieve all of this? So how do you get all these higher throughput with a low replica lag? So the main difference that we like to talk about is we focused in on working smarter, not harder, right? We always hear about this. So in the Aurora's world, what it does is it means we are doing less IOs. And so that minimizes a lot of the impact that you have. That's the most costly performance that you have, the bottleneck that you have with traditional databases. So fewer IOs means a lower number of network transmissions, which we cache prior to doing the results, and then we offload the results. So that way, for the results that we're going to be accessing frequently, it's already there, and you don't have to constantly hit the database. So also, we also do things asynchronously, which also helps out with the I/O performance. And we remove a lot of that context switching. We use lock-free contention, and we do a lot of batch operations. So here's our I/O profile. You can see over on the right-hand side, we have the MySQL. So we have about 4 different lines going down there, and those lines represent the different types of writes that you have. So you have buffer writes, you have FRMs, you have pages, et cetera. So quite a few that you can see how that would quickly add up on your I/O. Over on the left-hand side, you have Amazon Aurora, and there's exactly one type of write going on. And so we stream redo logs from the engine down to the storage node. And so if you remember when I talked about our storage, we like to make 6 replicas or 6 copies of your data. So essentially that means we're doing 6 writes of data. And even then, we still reduce the writes per second for the same amount of data. So lock management. So this is another thing that we worked on improving. And so over on the right-hand side, you have MySQL doing the lock management. And so what you have is you have a gigantic mutex in front of the lock manager for MySQL. So what it effectively does is that the transaction has to go to the mutex, and then it gets serialized by the lock manager to perform the transaction itself. So you can see anytime you're serializing your process, it slows things down. With Aurora, we just basically removed that portion of it. So with MySQL, we have a single global lock management in front of the lock manager, which is what was the limiting factor on MySQL. Instead, we replaced that with multiple connections that can access individual locks. So that way you can have all those different chains together with a single lock management. And we focused on improving all of this to optimize the performance. So that way we are going to be doing things in the future. And I think I read about bitmap compression and futexes instead of using spin locks. And don't ask me actually, what those mean. If you have questions about those, I'm sure Vlad can talk about that. But that's the nitty-gritty stuff behind the optimization that we have. Another thing is, instead of serialization, we have asynchronous key prefetches, which means that what we're trying to do is we started out looking on the latency of the engine. So last year, we implemented the asynchronous key prefetch, which is what we're doing is prefetching in the background on keys that we know that you're going to be accessing frequently. So this obviously helps optimize a lot of the performance as well. We show there queries 1 through 22, and it's the various performances that you have using the asynchronous key prefetch. So if you actually look at one particular query, query 19, supposedly got up to 14.5% improvement on top of without using the asynchronous key prefetch. I'm not getting into all the details around the benchmarking. I have them in the backup notes if you actually want to go into all the data around how we did it. We are using industry standards like sysbench for all of these benchmarking improvements. So for batch scans here, so batch scans is what we're doing. Instead of taking queries going one at a time, we're trying to remove all the contention from them. We do batch scans within the memory buffer, and this improves the latency for the query. So we use the same decision support system, which also significantly improves the performance as well. So parallel query processing. Do you guys understand what parallel query processing means? So parallel processing, right, is generally when you have things going multiple times instead of serially in a row. Generally, for traditional databases, when you're talking about parallel queries, what you're talking about is actually multiple threads. It's a multi-thread action that's being performed on the engine as they're running out your queries. So it's a multi-threaded approach to dealing with your queries. What we did with Aurora is that we looked at our architectural stack. And as I mentioned, we have our database engine, and then we have our storage layer. what we did was that the storage layer happens to be made of a bunch of servers in the background. So we should harness the computing power we have in the storage layer. So we took the queries from the engine, it pushes it down into the storage layer. In the storage layer, each of the nodes have tons of servers behind them, hundreds of them, and they're all on SSDs. So they have over thousands of cores attached to them, so vCPUs that we can harness to run all the queries. And then we take those queries, we perform them, and then we push the results back up the stack to the data engine. So that's how we perform parallel queries. So what does that mean when you're looking at the numbers? So using, again, the sys benchmark, we can get up to 120 times the improvement. So looking at those, again, it's the same queries, 1 through 22. You'll notice that 8 of the queries show a significant amount of improvement. What I liked here was actually reading about the Netflix quote. So Netflix, fairly well known, one of our largest all-in customers. So they tested out Aurora parallel query. And what I like to focus in on is that they were so much improvement on the performance side that they were actually able to reduce the instance types that they were using from an 8XL down to a 2XL. So that actually meant that they were able to reduce the cost and performance simultaneously by using parallel queries. So great for cost improvement. So all these performance improvement, they don't mean anything if your stuff isn't up and running. So let's talk about availability and what we did to improve in that area. Mentioned over and over again that we like to replicate the data 6 times out on our distributed storage layers. When we do a read, we do 3 out of 6 quorums on that. So it's a read quorum and a write quorum. And so a read quorum is considered successful when we generally have 1 read is necessary for reading, but we look at least 3 quorums to ensure consistency of the data. So if for whatever reason an availability zone was out, we know that we have consistent, correct information. Our writes are 4 out of 6 writes. And what that means is that when the write has been committed to the SSD, 4 out of 6 of them, we've considered that a successful write. So that guarantees, again, that high availability. Peer-to-peer replication in the background for the network performance so that we know that they're always in line with each other. If it happens that you have a slower performance for whatever reason in one node, it allows the node to catch up. Our volumes are striped across hundreds of nodes for performance. And again, this allows for, should you have an availability zone or a data center or something go down, that you have access to the other areas. Consistency of information. So read replicas and custom endpoint. We offer a master node and up to 15 replicas within them, so 16 total altogether. And so each of the read replicas are promotable to a master. On top of that, you can actually decide the order of how you're going to be promoting your read replicas. So for example, if the master goes down for whatever reason, and you have a replica that happens to be within the same availability zone as the master, you're more likely to want to promote that read replica for performance or where the application is. Yes, I have a question?
I have a question. Can you go to the old slide for a second?
Back one slide. Yeah. This one?
About, yeah.
Okay.
I'm confused about the 4 out of 6 right quorum.
Sure.
Let's say 2 didn't write properly. How do you know which ones are the ones? And when you want to promote from inactive to that, how do you make sure which one is to be taken?
So the question is, when for the write quorum, we say that a successful write is when you have 4 out of 6 writes acknowledged as successful. So if for whatever reason, what we're saying is we're not waiting for all 6 writes to complete. We're saying that as soon as there are 4 writes that are successful, that is considered a full successful single action. So the second part of your question is, how do we know if 1 or 2 of those writes were not successful? How do we know if they weren't successful? That's actually an excellent question. I don't know that answer. Do you know, Vlad? So Vlad he's actually our principal Aurora SA, so it's really handy to have him here.
So basically, the way that works is when you issue a write, when you change a row, right, we generate a change in your data page that holds that row. And that change gets sent to 6 storage nodes. When 4 of those reply back, we consider that write durable, because with 6 replicas and 4 of them confirming back, we always have a guarantee that at least there's coverage with the 3 out of 6 read quorum. At least one of the 3 that's reading will touch the new data and it gets the correct data out. The two of them that we haven't waited for on the right side, they may still come back with the successful response, but they might come back later, and we just decided not to wait for those 2 nodes, right? We only waited for the fastest 4 to respond back. If for whatever reason those writes don't complete on those particular storage nodes, we do have a gossip protocol behind the scenes on all the storage nodes that coordinate with each other and synchronize their changes and catch each other up with any sort of transactions or any sort of changes and redo log records that they have missed. Does that answer the question?
Yeah, so out of the cap, on the cap, consistency is one of the things, right? Now with this, the nodes are not consistent. And in the next operation or a previous operation, once before it's responded, okay, it did not do well. Okay, so they are still out of being consistent.
So the 4 out of 6 quorum guarantees at every time you make a data change that there's 4 nodes that have the correct data. 2 may or may not, potentially. Most likely they all 6 will have it, but 2 of them it's okay if they don't have it, because anytime we issue the write, we always ensure that that 4 out of 6 always ensures that there's overlap, right? You're never going to be in a situation where some of the nodes see some data and other nodes see other data. There's always going to be at least 2 nodes in that configuration that see all of the data, right? Even if 2 other ones may not overlap. So principally, the way our writes work is, compared to a traditional database where we write an entire data page to disk, right? Whenever you make a change, you change the data page, you mutate it, and then write that into the data file to disk. That's how most database engines work today, traditional ones. We only use the redo log. So the redo log is essentially a change vector. It's a binary difference between how the data page looked like before and how it looks like now. So we send that to storage, but that's also controlled using a sequence number. So anytime a subsequent write happens, that sequence number gets incremented. So we track the consistency of the storage using those sequence numbers. So we always know when a write was durably received, it's attached to a sequence number. So a storage node might have missed one write previously, but when the next one comes over, it knows that it has a gap in the sequence number that it needs to synchronize using its internal gossip protocol. Does that make sense?
Yeah, I understand it eventually catches up, but at any point of time in the transaction, we have the same issue on availability and consistency.
So there's a logical transaction aspect and there's physical quorum on the writes. So the transaction commit becomes effectively a change as well, a change record. So the storage will know when transactions were committed, and that's the consistency point of the storage. So it won't expose uncommitted data or uncommitted changes to other transactions, right? So the isolation still works the same way as in any database, because the storage does keep track using those sequence numbers. It knows what was durably stored versus what transactions were up to what transaction you're successfully committed. So there might be a discrepancy between those 2 points, right? Because there might be in-flight data that hasn't fully committed yet, but we know that and we track that. And we ensure the... All of the isolation levels that MySQL supports, for example, are supported in Aurora on the writer as well. Reader nodes are exclusively using repeatable read isolation. Yeah. On the readers. The writer can support all of the isolation levels. Default is a repeatable read. So it ensures that every transaction is isolated and doesn't see obviously any uncommitted data. It ensures also you don't have any phantom reads, for example.
Oh, the mic up. Oh, no. All right.
Yeah.
So thank you, Vlad. So with that, he covered some of the content I have in the future. So that's great. Gives you a little baseline understanding. So going back to this, so this is what we were talking about, Vlad, at a particular point when he was talking about your reader endpoints that we have. So one of the beauties of having reader is that you can have multiple reader endpoints. And what this means is that you can associate different groups of read replicas to these reader endpoints. So if your application that you have wants to only touch a particular grouping of read replicas, you can actually isolate it and say this application will only focus in on these read replicas, and this application will only focus in on these read replicas. Or you may want them to be able to access any of the read replicas, and that's the flexibility that you have with them. And as Vlad mentioned, that we do everything using a redo-based replication. And so it's a very lightweight protocol, and so it means that the read replicas are typically lagging less than 10 milliseconds behind. So instant crash recovery. The reader log allows for instant crash recovery with the implementations that we do. So checkpointing. Checkpointing is when you're basically writing about the changes within your databases. And so generally you might be doing checkpointing maybe, let's say, average of every 5 minutes or so. So within every 5 minutes, you're saying, this is what the database looks like, this is what the database looks like, this is the database what it looks like. But what it means that is if you have a crash and you need to recover from that crash, the last information you have is potentially up to 5 minutes ago. Then you have to apply the logs to it to catch your databases up. And you might then be doing more transactions in the meanwhile. So this will keep adding to it. So you're not taking 5 minutes to catch back up to current time. You have 5 minutes plus additional logs to apply to attempt to catch up to where you are at the current state. So Aurora does this differently. So in our case, the data is stored in pages where all the logs are associated with the page themselves. So all we have to do is reset the pointer to the page that was associated with the last consistent point. So by only having to move your pointers, you have a much faster and nearly instantaneous recovery so that when the logs are applied, only when the page is read. So this, again, allows for a really fast recovery, the near instantaneous crash recovery, as opposed to waiting for however long it was from the last checkpoint that you had. Continuous availability with multi-master. So this is currently in preview. We've been waiting for this for about a year now. So multi-master literally means multiple masters. So in a traditional database, or just in a database in general, you have your master node. And we talked about having replicas out there, right? And so everyone is taking the source of truth from the master. The master is the one that tells all the other replicas what's going on, and it holds all the changes. And so if there's any inconsistencies, we go back to the master. What you have with multi-master is you have 2 or more masters available to you. And so that sounds fantastic, except that you're adding the complexity to that. So we're gonna get into that a little bit more. So the goal of having multiple masters is, should your master fail for whatever reason, you already have an existing master already up and running, so that way it should be a seamless impact to your customers. They shouldn't be aware of what has happened from their perspectives. So what it means is a multi-master allows you to scale out your write workload. We use what's called an optimistic conflict management. So multi-masters, again, you have 2 masters. Both of them are saying, I have the source of truth. So say you are writing to a particular object or role, and it happens to be at the same time. So the optimistic conflict management says that most likely, there won't be contention. We assume there is little to no contention. And if there is a conflict, we will roll back the offending query. So that means that the two or more queries, when they collide, one of them will be successful. And we're going to talk about how we actually choose the success of it. So within Aurora, there are different ways of looking at it. So the simplest case, transactions with no conflict. The transaction originates from the same head node. The head node can be the arbitrator. So if the transaction is committed within the same storage node, then the storage node can be the arbitrator. If you have two different transactions coming from two different storage or head nodes, and they happen to actually involve more than one storage node, then you need to have an external arbitrator. So in this case, on the chart here, we have the blue master and we have the orange master. So they're writing to two different tables, and they happen to be on two different pages and using two different storage nodes. So in this case, there's no conflict, nothing to worry about, nothing to arbitrate on, and so we would proceed with the normal sharded workload. Moving up in your complexity is you have a physical conflict. So in this situation with the table represented here, you have two masters writing to the same table, and which is table 1 on page 1 on storage node 1. Then you're going to have a conflict. Everything's on the same theme. So what we do is we are using the quorum-based system that we have, and one of them will win the conflict. So in this case, the blue master will win out. And so basically, who is writing and checking in? So again, we said the write quorum is successful when you have 4 writes complete and acknowledge success. So in this case, the blue one managed to write 4 first, so they acknowledge, so the orange will actually get rolled back in this case. Does that make sense? All right. Oh, I hear a question. Yes.
How and why, how is the blue table is getting, the quorum is taking advantage? Like, what is that which is making the quorum getting fixed?
So the question for those of you on Twitch, thank you for being on Twitch, by the way. The question is, how was it determined that the blue master was the one that won out on the 4 quorum rights as opposed to the orange one? So I don't know the architectural behind it, but it's essentially whoever was faster to complete and get the 4 acknowledgements in there. So I don't know what made it go faster. There could be a variety of reasons. Could be latency. It could have been faster getting there, right? Because since we're talking about different masters, but they're using the same hardware, so one of the masters is probably not on the hardware, or it happens to be geographically located further away, so you have a distance issue getting there. So at the end of the day, no matter how much architecture and hardware, and there's still physics at the end of the day gating the exact right time. So chances are there was probably a latency and allowed the blue master to hit the 4 out of 6 first. Does that make sense before I move on? Could you repeat your question? How big is the page? So the page has 6, so 6 writes. We said that we do 6 replicas. We take the data and we replicate it out 6 times. So within a single page, you're always going to have 6 replicas. So the question is, how big is the actual size of the page within the storage layer? I don't know that, Vlad, my wonderful.
It's 16 kilobytes.
16 kilobytes is the answer for how large the page is. Is that helpful? So the question was, if you have 2 active nodes, so getting into the active architecture or the multi-master, it says one node has to be larger than the other one. How do you resolve that? Is that the question? So you look like you're ready.
So the size of the node doesn't matter as much, right? Because when you're realistically writing making a write, like you insert a row or update a row or delete a row, anything like that, what that generates is essentially changes to one or more data pages that are 16 kilobytes in size. So what happens in a transaction is each one of those data page changes is evaluated individually in order in which they were generated, right? Sent to the storage layer. The storage layer is going to, if it hits 4 out of 6 on that particular data page, it'll continue on to try to write the next one. If it doesn't hit a conflict, it'll go so on and so forth for all the data changes, and it'll respond back with a transaction completed, right, committed. If it hits any sort of inconsistency at some point because it couldn't write a 4 out of 6 quorum, it'll reply back to the engine layer and say, conflict. And at that point, your transaction is going to be rolled back, and your application has to resubmit that transaction and try again. So that, in a real workload, the scope of conflict can be, ultimately across multiple pages. We're simplifying things here. We're showing it, in the context of 2 pages, right? Or 2 transactions trying to write at the same time, just for simplicity purposes. But, the spectrum could be a lot wider. So what you need to kind of keep in mind is basically it means that from your user perspective, if you try to write and touch the same pages at the same time from 2 different writers, one of them will win, and its transaction is going to be committed. The other one will be forced to roll back the transaction using a deadlock message. And that's what the client application sees. And then if it gets rolled back, then your application has to have the code in there to actually retry again.
And this goes back to what we were talking about, the optimistic versus pessimistic. So with optimistic, you're always going to have a transaction completed. We will roll back one. With pessimistic, it means that both transactions, or however many, they will all roll back, and then you'll have to restart over. So that's the difference within the logic that we are applying. I saw one more question, and then I'm going to keep going because we have a few more slides on multi-master. So the question is multi-master Aurora similar to Oracle RAC? Anything else or just that? So I don't think it is, and I'm not an Oracle expert. Vlad, do you work with Oracle much?
Not entirely. We're taking a different way of handling concurrency and conflict resolution. So Oracle RAC basically is a technology where you have multiple nodes that are coordinating with each other on writes and keeping a consistent unified cache across them, right? All of them. We don't. The nodes in Aurora are completely independent of each other. The storage itself is handling the conflict resolution on your behalf. Sorry? The storage is common. It's a cluster-wide storage that all of the nodes see the same storage, and that storage layer is also responsible for the conflict resolution. Whereas in Oracle, you're having a more complex topology that also has a cache synchronization in there.
All right, so the beauty of having Vlad here is that as an Aurora specialist, he actually gets to work directly with the Aurora product team. So that's how he gets to have all this wonderful extra information that I don't know. In my role, I get to be a generalist, but Vlad is obviously awesome to have always here to get information on the background. So I was kind of given the 15-minute warning, so I'm going to jam ahead a little faster to get through the rest of the content, and then we'll save time at the end for the rest of the questions. So if you have more questions, you can ask us during the lab or at another point in time, just in the interest of time. So the last scenario for multi-master is the logical conflict resolution. And so this is the most complicated one. And so what it's saying is that you have 2 transactions writing to one page, page 1 and page 2, and they're both writing to the same table. So in this case, transaction 1 wins on page 1. Transaction 2 wins on page 2. So there isn't an easy way when you have 2 different masters and you have 2 different storage nodes. So we have to designate a tiebreaker in the scenario to break the tie. So here what we're looking at is we're looking at your commit latency. So again, going back to saying where the master nodes are in relation to where you're trying to commit to. You're always going to have a little bit of latency involved. And we're also looking at where your workload is in the situation. We found that this scenario is very rare. It rarely occurs. And so if it does occur, though, you are definitely going to see performance suffering because we're going to be working on the tiebreaker in that area. But like I said, based off of our testing and discussions with multiple customers, it almost rarely occurs. So I'm going to kind of skip through this a little bit. So in this scenario, we're just going to talk about the scaling out availability. So we're talking about 4 nodes here. And as you can see, as we're adding nodes to this, you can see an increase of performance. And so what we're saying is at some point, you're going to see a failure occur. And so the downtime, I think that's minute 12 or so, you see it go down, then go right back up. So that is basically how it's recovering when you have a failure within a node for the multi-master scaling. So applications also have global footprints. So we were talking about multi-masters. So another part of talking about this is generally when you're talking about multiple regions. How many of you have heard of Dynamo global tables? Or I guess I should start out. How many of you heard of DynamoDB? It's our NoSQL option. So within DynamoDB, we have something called Dynamo Global Tables. Well, Aurora Global Tables is essentially our equivalent for our SQL version. And so what it is, it's a multiple region replication. And so as companies have started to get larger and larger, they're having to maintain data within certain regions. So you hear a lot more about regulatory compliance. For those of you who happen to be working with customers and or having offices within the European region, the GDPR data regulation, right? So they require that you keep your data within the country of origin. Or China, they like to keep their data within their country. You have all these different countries where they're starting to say you have to keep your data within a particular region. So we have now Aurora Global Table, or Global Database. And so what it is your Aurora database is spanning multiple regions, and you have fast replication across. And then what you have is our dedicated infrastructure, which carries out the replication on our backbone to help ensure that the data stays within sync. So we do a lot of engineering in the background. And so, again, as I mentioned, you would want to use this for if you're dealing with data regulatory compliance, if you need to have extremely low latency, for the business critical workload. So maybe you happen to be working banking or finance or accounting or something like that, you can quickly fail over to another region. So database backtrack. So this was another feature that we recently released. And this is oh, I did not mean to do that. Let's put it that way. This is where you actually did something, you didn't mean to do it. Somebody did something, maybe they meant to do it, and you realize you didn't like the end result. And so this allows you to go backwards in time. This is your time machine. This is what allows you to do, instead of that point in time recovery, you can just basically undo that and go backwards really quickly. It takes roughly 1 to 2 minutes to use the functionality of it. So Aurora is easy to use. So another aspect that we like to talk about Aurora is the ease of use. And we did a lot of features around that. Performance insights. So performance insights, for all of you data nerds out there, is to give you a lot of data about your data. So it's those analytics that lets you drill down to see the performance of your query, how your queries are doing. So you can rank your queries in terms of the CPUs that they're using, how much wait time you're having, the delays of the storage. You can slice and dice it by the hour, by the week, by the year. You can keep your historical data up to 2 years. The first 7 days are free, so you have to pay more after that. But it allows you, at least from the free tier, you can run weekend analysis as to what's been going on. So it gives you a lot of information that allows you to make insightful decisions if you need to actually do more performance tuning or optimization on the queries that you have. Or maybe you're starting to notice a trend that this dashboard happens to be executing the same queries over and over from a particular region or a particular time. I'm going to skip through this, but Slalom, one of our partners, they did this amazing integration. They took an Alexa skill and they integrated it with Performance Insights, so you can actually do a voice control and command calling out various themes in there. There's a whole video on this. I'm just going to, out of time constraints, just going to skip it. If you're actually really interested in seeing the demo, you can go onto YouTube. It's out there, and you can watch the demo over there. So, and security is always important. Security, we always say, is ground zero, but let's face it. Most of the time, security is not at the front of every developer's mind, right? So we try to do a lot of security management on your behalf to remove a lot of that thinking away from you. So you don't have to immediately go, oh no, are we compliant with XYZ? So we do encryption to secure the data at rest, and you're allowed to provide your own keys to it, so that way you can ensure that we don't have your keys. These are your keys that only you have access to in the information. We have encryption level at AES 256. It's hardware accelerated. We make sure that we have encrypted cross-region replication. So not only is your data at rest, it's encrypted while it's going through to being replicated out to other regions. We have snapshot copies. They're sent using SSL. We have a lot of advanced auditing and logging, so without having to impact the performance of that. So we know that that might be an IO hit, but because, again, we segregated out our storage layer from all of that, it helps that. And we also have activity monitoring, so you can see what's going on within your databases. So industry certifications. Aurora. So I mentioned that we have a bunch of different types of Aurora. Well, 3 specifically. You have Aurora MySQL, Aurora Postgres, and now Aurora Serverless, which I will get into. All 3 flavors of Aurora meet all of these industry standards out there. So if you happen to be needing to deal with PCI data, or you're working on stuff with the government, it has to be FedRAMP, or you're in the healthcare industry, we have all those various certifications. Of course, the caveat is it's a shared security, right? So PCI, we are compliant, but there's still work you have to do on your half for the data itself. So just saying that, oh, it's PCI compliant doesn't mean that everything is compliant. Database activity monitoring. So this is what I was talking about, what we do to enable having that high-level monitoring without impacting your data. So we take the Aurora, we take the events, we put it into Kinesis streams, and we spread it out. So again, we're harnessing the full AWS services and making sure that we take away the activity from Aurora itself using Kinesis streams. It spreads it out. You can send your data out to either CloudWatch, or you can send it out to third-party consumers, right? So you might happen to be using McAfee or IBM Guardium or maybe Imperva, right? So whatever you want to use, you can send it out and look at your data and do all the analytics you want to do to understand what's going on within your databases. If you put it into CloudWatch, you have everything on the second half of the slide. That's what you can definitely do within CloudWatch. CloudWatch is our integrated monitoring solution. It allows you to look in, and you can go into CloudWatch, analyze it, look at your database clusters. You can export the data out to S3 for long-term archival purposes. So I talked about the performance insights that keeps your data for free for 7 days. Well, you can also take a lot of the data and then send it out into S3 and keep it there as opposed to paying for that feature. So just an option. But then once it's within S3, you can use our other services like Athena or QuickSight or anything else that you want to use to perform the analytics on all of that. So other ways to get into actually Aurora. So say you actually have existing databases and you said, okay, Amy, I actually like kind of what I'm hearing. I want to see what it's like to use Aurora, but I don't want to have to recreate my database. So we said, awesome. Let's make your life easier for you. So if for whatever reason you're starting out and you said, you know what, I've been in the Amazon world, AWS for a while, and so I'm actually using RDS. Great. We can take that snapshot and immediately ingest it in there, and then we will hydrate your database for you. You said, well, kind of been towing the line, you know, I have my database running in EC2, or maybe, you know what, I'm actually starting from ground zero. I'm actually on-prem. We said, that's okay. we can still take a snapshot of your database, of wherever it is, and we can take the binary snapshot, and then we will ingest it for you, and then we will apply the bin logs to catch it back up to the current state. So again, fairly easy. So let's take a look at the last one. So those are the first two was for your open source communities. So the last one, your commercial databases, right? So, and some other ones. So you have also Cassandra, DB2, MongoDB, SQL Server. Did I say IBM? DB2, yeah. DB2. Oh, yeah, I've worked with DB2 back in the days. Getting those off of AIX mainframes is not fun. Anyways, so for those, what we can do is we have a couple tools for that. We can convert the schemas for you using SCT, which is our schema conversion tool. And then we can import it using DMS, which is our database migration services. And so what we try to do is attempt to help reconcile the differences between the different engines, convert it into either MySQL or Postgres compatible, and then migrate the data on top of that. So we break it down into two different steps. So our tools that we talked about, I think I heard that Vlad had covered a lot of this in the beginning, so won't hash it out too much. Migration Playbook is your best practices. And then we have workload qualification, allows you to estimate how much time to perform all of this migration. Schema conversion I mentioned, and the native start point, so you can use those native tools for your databases. Then finally, serverless computing. How many of you guys actually understand what serverless computing is? How many of you guys would like me to do a quick one-liner on it? So we talked about managed services, right? We said we took away your heavy lifting from you. We said you don't have to provision your server. You don't have to maintain the server, put all those patches in, right? But at the end of the day, you're still in charge of parts of that server. You still have to bring that server up. You still have to bring it back down, right? There's still certain things you have to do with a managed server. So serverless means we said, we're taking everything away from you. You said, well, I just want to run this task for 5 minutes. Do I have to spend 10 minutes to bring up the server, run my 5-minute task, then I have to bring it back down? So serverless is essentially, we said, you want it for 5 minutes? Got it. You get it for 5 minutes, and you're going to pay for that 5 minutes and 3 seconds you used about it. So that's serverless in a nutshell. We do everything. We manage it. We apply the patches. We maintain it. We upgrade it. We do all of that. Serverless use cases. Why would you actually want to do it? So this is for intermittent workload. This is for things that you're not going to be using often. Maybe you just are testing things out. You have a variable workload, and so you only want to use it for that. You want to test things. You want to run it at night. It can be interrupted. You want to make sure that you are covering your full scale of different things, and it's on consolidated fleets multi-tenant. Getting into the background. So I'm going to let me see how many slides I have left. I have 5. So this is kind of how serverless works in the background. And what it is you're going to be pointing your application to request routers. Those routers, at this time, they're not connected to the database. Aurora is not turned on. So what happens is that at the time you put in a query, we have a warm pool of instances. We said, hey, there's a query come through. We're going to come in. We're going to pull it up. We're going to execute your query, and then we're going to go. So you pay by the second. And again, I apologize. I'm jumping through a lot of this. I just want to make sure that you see this. Here are some of the features that we have within Aurora. And again, this is the last slide that I have on Aurora Serverless. I apologize that we are out of time, but we do have time to take questions during the lab. I thank you for your time. Again, we can take questions during the lab period. I'm going to ask Vlad to come back up here. He's going to be running you through our next lab. So thank you, everyone. Thank you out there on Twitch. And again, I apologize for jamming through the last few minutes.